The equations of quantum mechanics predict physical phenomena with extraordinary precision, yet orthodox interpretations of those same equations yield paradoxes that border on the magical. We are told that reality, at its base level, operates on fundamental randomness. We hear that particles exist in multiple realities simultaneously, that they influence each other instantaneously across space, and that reality itself only solidifies when a conscious observer looks at it. These four concepts form the pillars of the standard quantum worldview, but the paradoxes they create stem from a deep structural misinterpretation. We are taking a system that is still actively undergoing structural closure, and we are demanding that it behave like a completed classical object. A theoretical model called the Atomic Continuum Ontology, developed by Philip Lillian, provides a way out of this trap. It resolves the categorical error without discarding a single established quantum equation. This diagram outlines the three-stage reality gradient. It maps reality's transition from undifferentiated invariant coherence to finalized classical closure. The middle node is the partial closure object, a coherent structure in a measurable regime, but not yet resolved across its available closure pathways. The quantum realm is not a domain of ultimate metaphysical mystery. It is simply a transitional band where physical reality is in the act of closing. To understand how a physical system can be partially closed, we need to look at the underlying mathematics supporting this framework, known as the theory of disclosability. These mathematics demonstrate how exact scientific laws can constrain a system while leaving specific possibilities entirely open. This schematic separates reality into two domains: the blue realization space, the underlying complete state, and the green disclosure space, representing the state we actually measure. Notice the dashed outline, the realization fiber. It represents the lawful possibilities left completely unresolved by our measurement. A scientific law can become exact. It can close long before the physical realization actually settles into a single state. Consider a Penrose tiling. The local mathematical rules strictly dictate how each piece connects. Those exact constraints generate a global structure that never repeats. The local rule is closed and exact, but the global continuation remains non-unique. This formal quotient fiber architecture applies directly to quantum mechanics. It provides a strict mathematical home for the details left unresolved before a final measurement. Observing unresolved possibilities in a quantum system isn't a failure of causality. We are witnessing a rigorous structural feature of a partially closed system. We can now apply this mathematics of partial closure to dismantle the orthodox illusions, starting with indeterminacy, the widely held belief that reality is, at its foundation, random. When physicists measure a pre-classical system, the mathematics yield a probability distribution. But this uncertainty does not indicate ontological chaos, it indicates pre-classical incompletion. In this quadrant of the framework, indeterminacy is redefined strictly as incomplete closure. What appears to us as fundamental randomness is merely the measurement of a system before it has stabilized into a determinate state. The second illusion is superposition. Popular science often explains this by claiming a quantum system literally occupies multiple completed realities simultaneously, the famous cat that is both alive and dead. Look at the diagram for unresolved closure pathways. In this model, the wave function does not catalog a multiverse of completed worlds. It represents the internal pathway structure of a partially closed object. Superposition is coherent closure multiplicity. It is one single coherent structure that has multiple unresolved directions available for closure. These pathways are entirely coherent, but they are not completed classical realities waiting to be chosen. They are potential routes toward a single reality. Quantum probability, therefore, is simply the statistical shadow cast by these unresolved closure conditions. By reframing indeterminacy and superposition, we eliminate the need for literal multiplicity and ultimate randomness. The predictive math remains intact, but the structural logic of the universe is restored. The third illusion is entanglement. Standard interpretation frames this as a mysterious, faster-than-light connection between two entirely separate independent particles. This paradox is caused by a classical assumption flaw. Physicists assume that the two separated outcomes we eventually measure were the primary independent starting objects of the system. This visual introduces the geometric solution, the bivector relation. It shows that entangled particles actually originate from a shared pre-closure unity. Here in the bivector equation, the wedge product symbol denotes a partially closed oriented relationship. It does not describe independent local vectors, but a single unified structure. When the selection operator is applied, meaning a measurement occurs, it acts upon that unified bivector. This selection process simply resolves the original shared relation into paired, separated outcomes. No information is transmitted across a distance because the particles were never separate to begin with. Measuring one particle naturally allows us to infer the state of the other, but inference is not transmission. Relation is prior to the vectors. Entanglement does not require hidden messages traveling faster than light. It is merely the geometric disclosure of a prior, unified relational state. Relativity is saved from the paradox. That brings us to the fourth and final pillar, the observer problem. Standard interpretation suggests that reality requires a conscious mind to collapse a wave function. Standard physics has failed to formally define what an observer actually is. The definition shifts arbitrarily between a human mind, a camera lens, or a measuring device. This quadrant of the framework introduces the structural replacement for wave function collapse, the closure selection function. As the text indicates, this function resolves an unresolved coherence field into a disclosed, measurable outcome. It is a universal physical transition. A wide variety of physical mechanisms can trigger this function. Environmental decoherence, a symmetry-breaking event, or a completely automated physical detector can all force a system to close. A conscious human can certainly participate in observation, but consciousness is merely one specific instance of a much broader physical process. It does not actively create reality out of nothing. The measurement problem is solved when we recognize that the only thing that matters is the actual structural closure function taking place, not the psychological status of whatever is performing it. Theoretical deconstruction requires empirical verification. To prove that quantum mechanics is the physics of partial closure, we have to look for physical signatures in the laboratory. We can test indeterminacy using weak probe protocols. A delicate laser can pass through a nebulous quantum field, extracting a faint data signal without forcing the system into a solid state. The objective is to gently probe the system's internal structure right before a strong measurement forces total state disclosure. The target signature in these experiments is called coherence residue. If researchers can detect a structured pre-measurement bias without fully selecting the final state, it proves the system possesses a partially closed structure. It is not purely indeterminate. The theory is strictly falsifiable. If our best instruments find no coherence residue beyond standard quantum predictions, the partial closure hypothesis would be severely weakened. We do not need to discard the highly successful equations of quantum mechanics. But we also do not have to accept absurd metaphysical illusions to explain them. By relocating quantum mechanics into the partial closure band, we preserve its predictive power. We can finally ground the mathematics in a rigorous, logically sane ontology of a universe in the act of closing.